So chapter 5. So what we have learned so far is one of the concept which is useful is like a molecular geometry. Is the most important thing. So the shape of the molecule. So the basic things we learned about are the three-dimensional arrangement of molecules, atoms in a molecule. So we learned some example. We have seen example of methane. So here is methane. What is the shape of the molecule? So it is called also called a molecular geometry. So you can see methane is a tetrahedral geometry. So you see all the four hydrogens are attached to the carbon atom in a tetrahedral geometry. So this is tetrahedral shape. Okay, and then we looked at some example of a neutral molecule, other molecule, boron trichloride. So here is boron trichloride. What is the shape of this? So this is an example where you see there are central atom is attached to three other atoms, and then this geometry of this is based on valence Vesper theory, which we learned, which is based on completely the electron pair repulsion between the all bonded electrons in this molecule. So here, and this is a trigonal planar geometry. Okay, and then the last example we tried is carbon dioxide. So if you look at carbon dioxide, what is the shape of this molecule? Again, it can be explained based on the Vesper theory, and you see the repulsion between the bonded electrons are between them and keeping the two oxygen atom away from each other, 180-degree bond angle. So this is the linear geometry. So that's a linear shape of the molecule. So these are the basic things we need to learn. When you have a carbon atom with a four groups or four different groups or four different atoms attached, it's always going to have a tetrahedral geometry. And then when you see boron with the three other atoms attached, it's a trigonal planar geometry. And then carbon dioxide is a linear geometry. Very similar way we can give an example instead of carbon dioxide, or you can put carbon disulfide, which is this. So you look at it, I replaced the outer atoms oxygen by sulfur, and that becomes still it's a linear geometry with a 180-degree bond angle. Okay, and the next is when you come down to this one, boron trichloride, I'm going to replace the central boron atom by aluminum atom. Aluminum is just underneath of boron, which is in the same group. Now that's going to be the same thing when you see aluminum with the three other chlorine atom will have the same geometry as boron trichloride. Here is the boron trichloride trigonal planar geometry. Here is aluminum trichloride AlCl3, which is again a trigonal planar geometry. Okay, so this is how you're going to understand, or you're going to relate to the shape of the molecule. If you know the one atom in the group, and then what is the shape with the three atoms? Example here, boron with the three atoms is a trigonal planar geometry, and then aluminum with the three atoms has the same geometry, which is trigonal planar. Okay, we'll come back to carbon, methane in this. So if you say, for example, you are going to replace by carbon by just simply carbon by silicon, replace carbon by silicon, any other group, just this generic example, I put X surrounded by the silicon. And if you look at it, this is will have the same geometry, which is tetrahedral geometry, as you see here. Question? Pardon? Do you have a question?
No, sir.
Okay. Okay, why does the shape of BS3 look a bit different from AlCl3? Okay, so yes, very good. Let me erase and put it the right way. Okay, so here is Cl, Cl, Cl. Okay, yes, thanks for asking, because sometimes, I was writing, I didn't see the difference between the way it's written. So that's how it should be written. It is trigonal planar geometry, which is 120-degree bond angle, and here is 180-degree bond angle. Here it is 109.5 degree bond angle. So that's the bond angle between different shape of the molecule and the atoms. Okay. Okay. So this is the basic thing. Now these are the three examples we have seen. Is a central atom with no lone pair of electron. Carbon does not have a lone pair of electron. Same thing with boron does not have a lone pair of electron, and carbon does not have a lone pair of electron. See, all these examples, the central atom does not contain a lone pair of electron. So this is, in this case, the molecular geometry is equal to the electron pair geometry, because 4 electron pairs are surrounded by the carbon atom, 3 electron pairs are surrounded by boron atom, and there are 2 pairs of each side, 2 pairs of electrons between oxygen and oxygen and a carbon, and then left side 2 pairs. So you see 8 pairs, 4 pairs of electrons surrounded by the central carbon atom, which again obeys the octet rule of having 8 electrons, except this is not an electron deficient molecule, which does not obey octet rule. Okay. So this is an example of a simple molecule where the central atom does not contain a lone pair of electron in a Lewis dot symbol. So this you can convert them into Lewis dot symbol by erasing the dash into a pair of electron, making it into a pair of electrons. So this is an example. Okay. So now we'll move on to the little bit of the second example where central atom with a lone pair of electron, and then we'll go to the next example. Any question? No, you don't need to know the bond angles of it. So we wanted you to know just the shape of the molecule. Okay. Okay. So the next thing we wanted to go over is in a molecule with central atom having a pair of electron, okay, lone pair of electron. Example. So here, ammonia, if you draw the Lewis dot symbol, this is going to be the Lewis dot symbol for ammonia, or the structure of ammonia, structural formula of an ammonia. So ammonia, this is the molecular formula, and this is the structural formula, the difference between them. Here is the molecular formula, here is the structural formula. So here is the Lewis dot symbol for ammonia. And now, based on the VSEPR theory, now you see we learned about this in class, because what we learned from the Lewis dot symbol for a molecule is there are the types of electrons involved in the central atom. The central atom, as in the previous example in methane, the only one type of electron surrounded by the carbon atom, which is a bonded electron pairs. Whereas when you see here, nitrogen atom has two types of electrons on it. One, a non-bonding electron, also called unshared pair of electron, and then the bonded electron. So there are 3 pairs of bonded electron and 1 pair of non-bonding electron. So what is the difference between a bonded electron and a non-bonded electron? The non-bonded electrons are higher in energy, and the bonded electrons are lower in energy. So the energy is very important component. So now you see what happens is the repulsion between the non-bonding electron and the bonded electron here, which is lone pair of electron, the pair of electron in the bond between nitrogen and hydrogen, is greater than the repulsion between the 2 bonded pairs of electrons. Same thing here. So because the repulsion is greater between the non-bonding pair and the bonded pair of electron, so these tend to be away from each other. The non-bonding electron and this hydrogen is tend to be away from each other. So now in this process, these bonded electrons are squeezes coming close to each other, because to minimize the repulsion between the non-bonding and bonded electron. So in this process, this adopts the conformation of 3-dimensional arrangement like a trigonal pyramidal geometry, like what you see here. So this is the trigonal pyramidal geometry here. So it's like a pyramid. You can see it's a trigonal pyramidal geometry. Please do not get confused with the trigonal planar geometry versus trigonal pyramidal geometry. Okay, so here is pyramidal geometry, like a pyramid. Okay, whereas there in the case of boron trichloride, it's a trigonal planar geometry. All of them is one plane of the paper. Boron, and there are 3 chlorine atoms are surrounded by them. Okay, But whereas here, so these all three of them are squeezed in one, and whereas the non-bonding electron is away from it. So this is the shape of the molecule. So this is the molecular geometry of ammonia, which has ammonia, the central atom as a lone pair of electron. Okay, that's one example. And second example, where you can see oxygen atom, water molecule in oxygen atom, where two lone pairs of electrons are there. Okay, so now that how does this works out? You see the same thing. There are three different types of repulsion between them. Okay, so here the repulsion between two non-bonding pairs of electron, and the repulsion between the bonding and non-bonding pair of electron on both the sides and left and right, and then the repulsion between two bonding pairs of electron. So if you see, this is the highest repulsion between the two non-bonding pair of electron, and this is in the medium where a non-bonding and a bonded pair of electron, and this is the least repulsion between them because those are in lower energy. So now considering the repulsion between a non-bonding bonding and bonding, and a non-bonding and non-bonding, so in order to minimize the repulsion between the two non-bonding pair of electron, the oxygen atom keeps the two lone pair of electron away from each other to minimize the repulsion between the two non-bonding pair of electron. And then also in this process, the two bonding pairs of electron between the two oxygen hydrogen bonds are close by, so it adopts a conformation called bent geometry. It's a bent geometry, and this is how it's going to be. So that's an example of water molecule, the shape of water molecule, which is the bent geometry. Okay. So here there are two things. All I talked about the molecular geometry, but I did not talk about the electron pair geometry. If we talk about electron pair geometry, it's a four pairs of electrons surrounded by central atom. Still, it's a tetrahedral electron pair geometry or electron group geometry. But when it comes to molecular geometry, this is the one I'm going to ask you in the exam. I expect you to know the molecular shape of the molecule. So of course, electron pair geometry is important to predict the molecular shape, but the most important thing is the molecular shape. So here is the trigonal pyramidal geometry is the molecular geometry. The electron pair geometry might be different, which is tetrahedral array. Same thing here. There are two pairs of non-bonding electron, two pairs of bonded electron. If you talk about the electron pair geometry or electron group geometry, which is going to be tetrahedral, but the molecular shape, molecular geometry is the most important thing in order to predict the properties of the molecule. So it is the bent geometry. Okay, so now having these two examples, then we can do the similar example. Say example, instead of nitrogen, you can put a phosphorus inside. So say phosphorus, and here a lone pair of electron, you will have the same geometry as ammonia. So all I did is I replaced the nitrogen atom by the phosphorus atom and kept all the three outer atoms like three hydrogen atoms, still have the same trigonal pyramidal geometry. Okay, and then on the other side, you see oxygen is a bent geometry. I'm going to replace hydrogen by fluorine. So here, replacing the two hydrogen by two fluorine atoms still have the same molecular geometry, which is going to be a bent geometry. Okay, so this is how you're going to understand the difference between a molecule with a central atom as a lone pair of electron and a molecule with no central atom with no lone pair of electron. So a big difference in terms of the shape of the molecule. Okay, one more example. Here is the ozone. So we can write the structure of ozone like this. So you can see one lone pair of electron and a central oxygen atom. So you see the way I drew, this is the bent geometry because of the lone pair of electron. The repulsion between this is greater than the repulsion between the bonded electrons between this bottom. So in order to minimize that, so the bonded electrons coming close, so it adopts the bent conformation. Another example of a bent molecular shape is ozone. Okay, same way you can see similar examples of molecule and then find out what is the shape of the molecule using this basic concept involved in a molecule with lone pair of electron and a molecule with no lone pair of electron at the central atom. Okay, any question? Yes, trigonal pyramidal, 3 bonding and 1 lone pair. Yes. So trigonal pyramidal geometry has a 3 bonding pair of electron, 1 lone pair of electron. Yes, that's correct. Okay. Is it tetrahedral or trigonal pyramidal? Okay. So for this one, the molecular geometry is trigonal pyramidal geometry. The electron pair geometry is tetrahedral geometry. Okay, there are, see, when you have a central atom with a no lone pair of electron, the molecular geometry equals the electron pair geometry. But when you have a central atom with a lone pair of electron, that's where the two different types of geometry comes. One, an electron pair geometry, another one is a molecular geometry. So the electron pair geometry for this is a tetrahedral because there are 4 pairs of electrons surrounded by nitrogen atom. Whereas the molecular geometry is trigonal pyramidal geometry. Okay. Okay. What is one on the top right? That's ozone. Yes, that is ozone. So can you able to read this? Because I wanted to make this a small board which I got it from, borrowed from my friend, and I wanted to know whether this board is, can you able to see clearly the structures? If not, I will make it a little bigger for you. Okay, good. Thank you. Thank you, Elizabeth. Okay. So the next thing is we are going to use, let me erase this. You guys can chat for a while, okay? Let me clean this one. You can unmute it and chat if you want to see your friends and socialize a little bit, that's fine.
Yo! Sorry, I yelled.
Okay, so the next concept, can I start?
Yes.
Okay. Okay, you guys should have some fun too. I know it's lonely being alone, right? It should be, okay, good. Anyway, that's fine. Okay, so, okay, I have a, now I'm moving on to the, you can mute now. I'll have one more concept and then we'll stop from there. Okay, guys? Okay, so there are two things. Now we are going to move on to the molecular properties based on the bondings. So we have learned two things. One, in the previous chapter and this chapter, we learned about a polar and a non-polar bonds in a molecule. And second thing, we learned about the molecular shape. So these two things is important for us to predict the properties of the molecule. How does the molecule behave? What is the property of this molecule? How can I know what property this molecule has? Okay. For example, solubility is one of the most important thing. How does this molecule soluble? How can I predict this molecule is going to be soluble in water or oil soluble or something in between? Okay. So that's something important. And here, so first thing, to see a molecule is polar or non-polar. A polar molecule, more the best example I can think of is water molecule, which is polar, which will solubilize most of the stuffs. Okay, most of the polar substances will soluble in water. Most of the non-polar substances will not soluble in water. Okay, so now our job is to predict the polarity of the molecule. First, we talk about the bonding of bond polarity, and then we talk about the molecule polarity. Okay, so now in order to see a molecule is polar or non-polar, there are two things we need to know. One, the bond, there should be at least a one polar covalent bond you need to see in a molecule. So for that, you need to draw the Lewis dot symbol. Okay, so I will draw the symbol and explain to you. And then the second example, for the molecule to be polar, first condition, it has to have a a polar covalent bond. You all know what covalent bond means. A covalent bond is between sharing of electron between the two atoms. And a polar covalent bond is between, there is a electronegativity difference between the two atoms involved in a bonding. It's called a polar covalent bond. So for the molecule to be polar, it should have a one polar covalent bond, right? Polar covalent bond. Oh, polar covalent bond. Sorry. Okay. Let me write a little bigger. Polar covalent bond. The second condition is the molecule must not have a uniform distribution of electron cloud. Okay, so how does that work? Okay, so non-uniform distribution of electron cloud. In other words, distorted electron cloud. Distorted electron cloud. Okay, so let me give you an example, a very simple example. How do I know this molecule is polar or non-polar? For example, here is a simple example again, methane. So now use the condition. See if this molecule contains a polar covalent bond or not. Yes, there is no polar covalent bond in methane. So the first condition does not satisfy. Okay, condition number one is not satisfied by methane molecule. The second condition, that's where the molecular geometry comes into it. If you look at this is the tetrahedral geometry, all four corners of tetrahedral geometry equally distanced. Okay, so if the electrons clouds are uniformly distributed all the four sides of it, so there is no electron cloud distorted one or the other way. So it is uniform distribution of electron cloud. So it does not satisfy the second criteria for the molecule to be polar. So in this case, this molecule is non-polar molecule. So this is an example of a non-polar molecule. Okay, let me see. Distorted electron cloud, which says the electron cloud is uniform, not one side is more and one side is less. I'll give you an example in the next few minutes with a polar molecule. Okay, so the next example here. So water molecule here. So here is the water molecule. That is the shape of the water molecule. That's why the geometry is important. And here is the two lone pair of electrons on oxygen atom. So now, if you look at the first criteria, a polar covalent bond. So a molecule must contain at least one polar covalent bond, but that's the first criteria, first condition. So now, if you look at it, oxygen and hydrogen bond is an example of a polar covalent bond. The difference between the electronegativity falls between 0.5 to 1.9. So electronegativity of oxygen is 3.5 and electronegativity of hydrogen is 2.1 and the difference is 1.4. So electronegativity difference delta En equals 1.4. So that's an example of a polar covalent bond. Yes. So yes, the first criteria matches with it. So it should be a polar molecule. But you also have to match the second criteria is matching or not. So that's where you come up with and see if what is the shape of this molecule. That's a bent geometry. But where is the electron cloud is distorted or uniformly distributed along the water molecule? Let me erase this and put it back, the two lone pair of electron for you. So here is the two lone pair of electron. So if you look at the electron density of the molecule, so the electron density is more on this part of the molecule, the electron density less on this part of the molecule. So you can place the delta plus on this side of the whole molecule and the delta minus on the top portion of the molecule. So now the electron clouds are distorted, non-uniformly distributed. Now this molecule is polar molecule. So that's how you understood the electron, the difference between the distorted electron cloud or not. So here, the oxygen atom is more electronegative. There are lots of electron clouds, lots of electrons, whereas hydrogen atom has a less electronegative. The electron clouds on the bottom portion of the molecule is less. So the electron clouds are non-uniformly distributed. So that's an example of a polar molecule. Okay, so these are the two important molecules. One here is an example of a non-polar molecule which does not satisfy these two conditions, having a polar covalent bond and having a distorted electron cloud. And the second molecule, water molecule, which matches with the both example, it does contain a polar covalent bond, and also it has the distorted electron cloud based on the molecular geometry. That's why the molecular geometry is important. Okay. So the next example. So any questions about this? Any question? Okay. So now I have a couple of different examples for you. Okay, so now we are moving on to something in between. Okay, so here's an example. Okay, carbon dioxide. Okay, is this molecule is polar or non-polar? This is the, we know this is the Lewis dot symbol, or this is the structural formula, and also it has the linear geometry of it. And you know, you don't need to worry about the electrons on the oxygen atom. Okay, don't worry about the electrons on the oxygen atom, which is not important to predict the shape of the molecule. So all you have to do is, what is the property of this molecule? Is this molecule is going to be, excuse me, a polar or a non-polar molecule? Okay, so here is again, let's follow the rules. The first rule is, for it must contain at least one polar covalent bond. So here is a polar covalent bond between a carbon and oxygen. Whether it's a double bond or a triple bond does not matter, but you see the difference between the electronegativity of carbon and oxygen must fall between 0.5 to 1.9, then it is called a polar covalent bond. So here is, let me put it delta En, electronegativity difference between them is 0.5 to 1.9, which means polar covalent bond. Polar covalent bond. All you have to see is the difference between the electronegativity of atom. So electronegativity, I know this on top of my head. So here is carbon, which is electronegativity 2.5, and then oxygen is 3.5. The difference between them is 1. So that's an example of a polar covalent bond. Okay. So the next thing is, I'll stop in a few minutes. Okay. And then we'll ask some questions we have, and we'll continue on the next one. Okay. So here's an example. You look at it, yes, this does contain a polar covalent bond. It satisfies the first criteria. It does contain a polar covalent bond between a carbon and oxygen. The second thing is you have to think about the electron cloud. Is uniformly distributed or it's a distorted electron cloud? So all you have to think about is, okay, so think about, I'm reading your chat box also if you have any questions. Okay, that's why there is a break in between. Okay. So look at next example. So the electron, this molecule is a linear geometry where you see both oxygen atoms attached to a carbon with a 180-degree bond angle. So the electron cloud along this molecule is uniformly distributed. So you can't place one side more electron, another side less electron, because both are equally electronegative. So you see oxygen atom on both sides pulling an electron away at each extent. Okay, so electronegative atoms tend to pull an electron equally. Both are pulling electron equally. So now there is no uniform, there is no distorted electron cloud in this. It's uniformly distributed. So this is an example of this. The second condition does not match. So I put no. So now this molecule is a non-polar molecule. Even though it contains the polar covalent bond, matches the first criteria, but the second criteria does not match, having a non-uniform distribution of electron. So here is the uniform distribution of electrons. So this is an example of a non-polar molecule. Okay, a small twist to this molecule. I'll make another molecule and then see what happens to the properties of that. Okay, so here's an example of another molecule here. So you see, one side is an oxygen attached, another side is sulfur attached. Now, is this molecule is polar or not? Yes, this molecule is polar. How can you say this? Okay, so here is an example. Does it match the first criteria? Yes, it does match the first criteria that polar, it does contain polar covalent bond between a carbon and oxygen, and the same thing on the sulfur and the carbon. Okay, so you see sulfur on the right side, oxygen on the left side. The second criteria is this a uniform distribution of electron cloud or non-uniform distribution of electron cloud. Here, the electron cloud is non-uniformly distributed because the oxygen is pulling more electron towards this side because oxygen is more electronegative, whereas sulfur is less electronegative. So you see the extent of electronegativity plays an important role. This is higher electronegativity, pull more electron, so the electron cloud is more on this side, it's a delta minus, where electron cloud less on this side as a less electronegative. Now there is a non-uniform distribution of electron cloud. In other words, it's called distorted electron cloud in this molecule, making it a polar molecule. Okay, so you see a small difference in a molecular structure makes the property very different. This will be very well soluble in polar solvent, whereas this is not. Okay, so that's a big difference between the properties of the molecule by changing one atom, and it's the property changes. Okay, so that's how you understand the properties. We'll talk about more example of polar and non-polar molecule. Meanwhile, I would like to chat with you guys to have any feedback or any questions, and you are always give a feedback. I will be very happy to hear from you guys, and we'll try to make what the best I can do for you guys. Okay, let me know if you have any questions or anything, and I'll be happy to explain. And if you want to leave the meeting, that's perfectly all right too. If you have any other commitments, you can move on to. You can leave the meeting at any time.
Bye. Have a good day.
Oh, you too, Dorian. Take care. Bye. Stay safe.